Hello, students. Welcome once again to Chem is Try. In our previous video, we learned about the factors that affect the stability of a nuclide. Proton to neutron ratio, binding energy per nucleon, number of nucleons or mass number. Then we also talked about half-life of a radioactive nuclide. In this video, we want to look at what we call radioactivity. Radioactivity is the spontaneous decay or disintegration of an unstable isotope with the emission of radiation and energy. Remember we said when a nucleus is unstable, it will do whatever it has to do to become stable. That whatever that isotope will do to become stable is what we call radioactivity. Here are the key components of radioactivity. Let's represent the key components with an example. In this example, we have an isotope of carbon called carbon-14. Carbon-14 has 6 protons and 8 neutrons. When you look deep, you realize that there are more neutrons than protons. So this isotope is neutron-rich. And what did we say about neutron-rich isotopes? Yes, they are unstable. So what radioactivity is telling us is that since this isotope is unstable, it will on its own, hence the word spontaneous, on its own decay or disintegrate. And it does so with the idea that it is unstable, so it wants to form a stable isotope. What stable isotope are we going to form? We have an isotope of nitrogen over here, and in this isotope, we have 7 protons, and the number of neutrons, 14 minus 7 will give us 7. So after this neutron-rich isotope disintegrated or decayed, it formed a more stable isotope. Why do we say it is stable? Remember, when the number of protons is equal to the number of neutrons, the isotope is usually stable. And that is what we are seeing over here. So this isotope is stable. Then we can see something attached to it. This is called a beta particle. And this is what we call our radiation. This spontaneous decay is the reason why we say radioactivity is also known as natural radioactivity, because it is not caused. The isotope looks at itself and realizes that there's something wrong with it. Either it is neutron-rich or proton-rich, or the binding energy is smaller, or it has a smaller half-life, or it has too many nucleons. Whatever the problem is, it doesn't want to stay unstable. So it has to do whatever it has to, which is spontaneously done. It does so on its own. Nobody will cause it. And when it does so, it will form a relatively stable isotope. But not just that. Energy and radiation would follow. And we can see radiation following over here. And normally we have energy too following this kind of reaction. But you can choose to ignore writing the energy in the equation. But we know that whenever there is any radioactivity occurring or a spontaneous decay occurring, energy is also released. This is what we call natural radioactivity. Since we have natural radioactivity, it also means we will have what we call artificial radioactivity. Then what is artificial radioactivity? So artificial radioactivity, it is the bombardment of a stable nuclei with a fast-moving particle. These fast-moving particles are also energetic to produce isotopes that are usually unstable. What we do in artificial radioactivity is that we have an isotope. This isotope is very stable. Then what do? We look for a fast-moving particle, which is also energetic. Then we will slam it through the stable isotope. And when we slam it through it, it will cause the stable isotope mostly to become radioactive in nature, which means they are going to become unstable. So when the fast-moving particle enters the stable isotope, it forms another different isotope. And we are saying this new isotope we are forming is usually unstable. And this artificial radioactivity is also accompanied by great amounts of energy and sometimes some radiations. For instance, look at this isotope of nitrogen we illustrated earlier. It has 7 protons and 7 neutrons. Very stable, because the number of neutrons and number of protons are the same. Very stable. Left alone, it wouldn't decay. It wouldn't undergo any radioactivity because it likes the way it is. But we are going to shoot a fast-moving particle through it. For example, this is called an alpha particle. We'll talk about these particles very soon in another video. Then, we will form another isotope. This is an isotope of oxygen, right? It has 8 protons. Then the number of neutrons is 9. Now, we've moved from stable to unstable. Then, sometimes, as we said, another particle is also released as a result. In this case, a proton. So, in artificial radioactivity, our isotope is very stable. Then, we are going to shoot a fast-moving particle through it to cause it to become angry by forming what? An unstable isotope, which will later decay to release energy and radiation. This is artificial radioactivity. Someone might ask, why do we need artificial radioactivity at all? This is how some elements are created. Elements like the trans-uranium element, the elements after uranium, most of them are produced artificially. And how do it? They take uranium and they will shoot a fast-moving particle through it. When the fast-moving particle sticks, it's either the number of the protons is going to increase, or the number of protons and neutrons are also going to increase, forming a different element. Remember, the moment the number of protons increase, we have a different element from the one we started with. For example, if we have uranium with atomic number 92, then we shoot a fast-moving proton through it, and it sticks. The number of protons will no longer be 92. It will increase to 93, which is a different element. So we've created a different element. If we are to shoot an alpha particle straight through uranium isotope, and it sticks, an alpha particle is coming with 2 protons and 2 neutrons. The number of neutrons will increase by 2. Number of protons will also increase by 2. We formed a different element with atomic number 94. So this artificial radioactivity is used to create new elements. And that's the uses of the artificial radioactivity. Well, in our next video, we'll be looking at the particles. Then we'll talk about the emissions involved during radioactivity. Remember we said When an isotope spontaneously disintegrates, it releases radiation and energy. Those radiations, you'll be looking at them. And in what cases do certain radiations get emitted during radioactivity? Thank you.